Okay, so we're going to go on to flux and generators. And this section's a little bit harder to explain everything quickly or in one sitting. So I think you're going to have to do individual questions to get over this. Sorry about that, guys. But I can go through a few of the basic ideas. So first of all, flux. Flux is area times field. Basically, it's a way of imagining how strong a field is in a section, or a loop. Okay. So if we look here, how much flux is going through there? Well, you imagine all the field going through. There's no flux going through A. Now imagine all the flux going through here. Yeah, there's pretty much all the flux is going through B. But over here, some of the flux is going through. So how much flux is going through? Well, essentially, we need to get, so flux, formula is flux equals BA. But then here we have sine theta. And the angle we need to get is this theta. Because really, if you think about it, the only part that's letting the flux through is the height. And the height equals the area times sine theta. So that's why we have this theory. That's why we have this rule. And then we get BA sine theta. So in this question, flux equals BA sine theta. So in this question, our field is 2. Our area is 0.02. And our angle, so it's the angle from the horizontal. Theta equals angle from horizontal. And it says there it's 45 degrees to the vertical, but that's also 45 degrees to the horizontal. So that equals sine 45. So we end up with 0.04 sine 45. So having a look at that, it should be about 0.03. And that's how you do questions like this. One, you look at B, you look at the field, you look at the area, and then you think about the angle. Okay, and that's how you get flux. So full 0. So the flux here would be just basically B times A, because everything's going through. So it becomes 2 times 0.02. And there flux would be 0, because none of the magnetic field is going through that little loop. And that's how you use the flux rule. So that's easy peasy. Next is Faraday's law. And this is basically, what they found from this is they figured out that if we have electricity in a field, then we could get something moving. So generators is if we have something moving and a field, we can get electricity. Basically, it's backwards. It's a backwards rule, and that's why we need flux. So let's do it in this question. Here's our little diagram. We have a field, we have little loops. There's 3 loops, that's important to note, and it's connected up to a little section. So to get any current happening, we need a change in flux. Current and voltage. To get any EMF. To get EMF, we need change in flux. We need require change in flux, or change in flux. Well, that's change. Okay, so here we know our original flux, and the magnetic flux through 120 turns of coil. Actually, there's 120 turns, not 3. 120 turns of coil. It's a constant for E times 10 to the negative 4 Weber. So flux, our initial flux equals 3 times 10 to the negative 4. And now it's reduced down to the 0. Final flux is now equal to 0. So a change in flux equals this, subtract that. Okay, now our formula for EMF is EMF equals negative n change in flux over change in time. That D is basically the same thing as a triangle. So our EMF equals negative n change in flux, which is 3 times 10 to the negative 4, of a change in time, which is 0.01. And now we need our n, that's 120. And what do we do about the negative? Basically just ignore the negative. That's why we have Lenz's law. So don't ever worry too much about the negative. And we multiply all this together and we should get 120 times 3 times 10 to the power of negative 4 times, oh wait, oh, how do we go back? I can't do it. 3 times 10 to the power of -4 divided by 0.012 times 120. We get 3 volts, and that makes perfect sense. So that's how you do it. So that's Faraday's law. It gives us a voltage, and this is just a little example of that. Finally, Lenz's law is the confusing one. So with Faraday's law, it tells us how much, but Lenz's law tells us the direction. That's basically the distinction. Faraday's law gives us a voltage out, but Lenz's law tells us which direction it's going to flow. So what we need to do first is think of 3 things. The questions to ask are, is the flux is increasing or decreasing? So in this situation, as the field is being decreased or reduced, our flux is getting smaller. Next, which direction is the flux going? So we know first flux, I like writing it down, it's getting smaller. So it's smaller. And it's going in this direction. So it's like it went from a huge arrow this way, to a tiny arrow. So we need to stop that. We need to compensate for that. So we need to give it a bit of a push, make it go this way more. So that means the induced flux must be to the right. So we get an induced flux for that. We'll counteract. And then to figure out the direction of the current, we just use the reverse right-hand rule. So if the current is going that way, I put my fingers in that direction. Then I put my thumb around the loop, so I'm facing down. So now going to the right is the flux, and going down is the current. So the current should be going this way. So it should be going from Q to P. So the 3 steps again to go for. First, is the flux getting bigger or smaller? Okay. And if the flux was getting bigger, we'd be going from a small arrow to a big arrow. Okay. And it's going in that direction. So we have to decrease it. So we have to go this direction. Okay, and if it was going that way, then we put our fingers into the loop, because that's the direction of the flux. And now, just like before, our thumb is always our current. We can see that the current will be going in the opposite direction. So anyway, for this one, it will be going from Q to P. And this is Lenz's law, because Lenz's law gives us direction. Okay, and that's probably the more confusing one. I'll go through a few examples in the book, but here's a tiny little example. If we had this going out, we could check the first thing, is the flux getting bigger or smaller? Well, the flux is getting smaller. Next, it's going from top to bottom. So if it's getting smaller in this direction, it's getting smaller. So it was really big and it's getting small. I have to give it a bit of a push, so I need to push it down. So I put my fingers, because that's my field and my flux, and then I put my hand around that little loop, and we can see that the current must be flowing in an anti-clockwise direction. Okay, and generators, essentially backwards motors, you can use the same kind of theories. I'd like to see if I could give you an example. I think at this stage you're going to have to be doing some practice questions. I might just go through this question. So this is the same diagram, and this is a change in magnetic field. So this is a change in flux. What would the current, or what would the EMF look like? So the question asks over here. Sketch a graph of the voltage against time. So EMF is also voltage. So voltage equals change in flux over change in time. So here the flux is increasing quite a bit, negative n, but don't worry about that. It's increasing quite a bit. Okay, so we can make it go negative if you want. So for this section, the change in flux is quite steep. Okay, and then here there's no change in flux, so we have no voltage. Then finally over here it has to be in the opposite direction, but it's not as steep as before. It's decreasing like it's actually half, because the decrease is over twice the length. So we'd expect something to look like this. And that would be your answer for this. I hope that makes sense. I'll go through all the questions in the exam papers, which should make more sense there if you're a little bit confused. But I think this cheat sheet should help out a bit. Okay? Cheers, guys.